Yes. Okay. So thank you for this invitation. I would have also liked to be in Buenos Aires, like I guess many people, but well, it's not possible. So yes, I'm going to talk about balanced excited random walk actually mainly in dimension 2. And this is a joint work with Omer, Angel, and Mark Holmes. So, well, this is a. I will begin with a definition for any dimension. This is a discrete. It's a discrete time random walk. Which is moving on the lattice. It was introduced by, well, I think yes, Benjamini, Kozma and Shapira in, I think it was 2011. So it's a discrete time random walk. I will explain how you define this. And there are 3 parameters I will need. So one is the dimension of the lattice, but then I will need 2 other integers, which are also dimensions in a sense. These 2 integers will be between 1 and d. So I will also use the standard notation. These will be the canonical vectors. So how do you define this? The thing is that there is a rule where the walk uses the first d sub 1 coordinates or dimensions. Let's say that, let's use the word dimensions here. And it is simply that if the walk, in words, if the walk visits a site for the first time, it jumps to nearest neighbors uniformly, using only the d sub 1 first dimensions. So if you didn't follow exactly what I said, I'm writing it here as some transition probabilities. So the probability that I jump in direction e sub I, given all the history of the random walk and given that I didn't visit any site, given that site n is, at time n I'm visiting a site for the first time, is just 1 over 2d in all the directions, d1, sorry. And for the last coordinates, d2 coordinates, what the rule is simply that if I visit a site, an old site, I will now use the last d2 coordinates. and you can write this in a similar way as I was writing it before. So now the condition is that at time n, I'm visiting a site which is old. And again, I jump uniformly to all the nearest neighbor sites. And okay, I will this is a notation that some people have used. I will adopt this notation. I will call M sub D, D1, D2, the corresponding random walk. So, well, some examples just to maybe have a little bit of a more concrete view of what's going on. This is the M211. This means that the walk I could adopt. It depends which coordinate you call the first coordinate. So if you call the vertical coordinate the first one, in this case, the rule is that when I visit a site for the first time, I jump vertically with probability 1/2 up or down, and for the second and later visits, I jump horizontally. So I want to point out that in this definition, you might have a overlapping, I mean, D1 plus D2 not necessarily are equal to D. So I can consider, for example, this case, M432. So this means that for first visits, I use the first 3 coordinates. For later visits, I use the last 2 coordinates, 2 dimensions. Okay. So let me mention some known facts about this model. Not so much is known. I will separate this in the case in where the dimension is equal to the sum of D1 plus D2. So let's call this the non-overlapping case. So it's not difficult to see that if the dimension is large enough, if actually the dimension is larger than 5, then the walk is transient. And this is simply because if D is larger than or equal to 5, either D1 or D2 will be larger than or equal to 3. And well, you have to justify a little bit more what I'm saying, but this means that there will be some set of 3-dimensional coordinates which are visited an infinite number of times as a simple random walk in a different time scale, and this will give you the transients. So as I said, this means that one of these is larger than or equal to 3. Well, I would say one of the first non-trivial result was in dimension 4 by Benjamini, Kozma and Shapira, and the paper where they introduced this, and they showed that the M4 to 2 is transient. There was then another interesting result of Perez in dimension 3, Perez, Shapira, and Susi. And they show that the case M312 is transient. So M312, okay, this means that old sites use 2 dimensions and new sites one dimension. So yeah, so you have, okay, old sites 2. Then in the case where there's overlap, so I mean D1 plus D2 larger than D, we looked at this with Camarena, Gonzalo Panizo, and myself recently. This was actually, it's in the proceedings in the memory of Ladas, it's published. So we show that whenever this set of parameters is different than 4, 3, 2, then the walk is transient. I'm not going to comment so much about this. Maybe just say that when the dimension is larger than or equal to 7, this is quite direct. Because when there's overlap of dimensions, well, I can define this new number, which is this number R, which I'm calling R, is the set of dimensions which are used, which are common for new and old sites, and essentially you can see that whenever R is equal to 3, or D1 is sorry, R is larger than or equal to 3, D1 is larger than or equal to 3, or D2, then you will have transients. And this means that the only, well, that corresponds to D larger than or equal to 7. So the cases where, which do not satisfy that necessarily happen when the dimension is smaller than 6. I can even write this, you see D is D1 plus D2 minus R. You can write this as D1 minus R plus D2 minus R plus R, and this is smaller than 6 if none of these conditions is satisfied. Okay, now there are many open questions about this this model. I will mention some of them here. So the first one, which is still open, is whether or not the 2-dimensional model, the random walk, is recurrent. Another one, which is still open in dimension 3, is whether the 2-1 case is transient. And even even in the overlap case, the M432 case, okay, if this is transient or not. The 2-3 case is covered by what we did with Daniel Camarena and Gonzalo Panizo. And another question, which is I will address in this talk, is for the 2-dimensional random walk. Let me say it like this first. Asymmetry of the range. So let me see if I have a picture here. Yes, I have it actually here. I'm going to move it. I'm not so good at this, but okay, maybe. Sorry. So I cannot find the picture now. Let's see. Yeah, so I will show it here. Sorry. So this is a simulation of the two-dimensional random walk. So this is the M21 random walk, and for 10 to the 7 steps. So you can see it's the range, and this is the picture of the number. The black region is the range of the random walk, and you can see that it tends to be much extended horizontally than vertically. So actually, that's the question that I am formulating here when I say the asymmetry of the range. So, right, should be something like this. And, well, now it turns out that the frequency with which the random walk visits old sites is, well, you can show that the density of times with which you visit the old sites is positive, uniformly positive. So this means that the range of the two-dimensional random walk horizontally should be more or less of order square root of n. But the vertical movement, the number of steps you make vertically is equal to the cardinality of the range. So let me call Rn the range, and maybe little Rn its cardinality. So as I say, the number of vertical movements is equal to Rm. So and on the other hand, the movement that the random walk makes vertically is balanced, so it can jump up or down with the same probability. So this means that the length of this vertical range should be more or less square root of Rn. So if you want to address question 4, it would help, or it would even be enough to show that the range of this random walk is a little O n. And then you would get this asymmetry. So of course, well, if this was a simple random walk in dimension 2, this is it is trivial. The range, everybody knows, is more or less like n over log n. But here, you have this non-Markovianity, and which you cannot. So let me state the main theorem I want to, yes, and so we have actually an upper bound and a lower bound on the range. This is the upper bound. And I'm going to state this here in expectation. You can say this also, make a statement in probability. But so the expected number of sites visited actually it is little O of n. We were able to obtain this bound, the log n. There's a constant here. Which is, I will explain you why this actually is not. We believe it's far from the right behavior of the range. For the lower bound, we have a something which is some constant n to the 4/7. Maybe, yes, I think we have to put a log here. This is not so important. N or n to the power of 4/7 it is the important. Okay, so this shows that actually you do have this behavior that the range is little of n, so the range is asymmetric. Of course, this is the two-dimensional case. So let me make some comments here about the. Well, 4/7 is more or less 0.57. But according to numerical simulations, this range should grow like, well, according to n to the alpha. And so this is a, well, only numerical simulations, and with an alpha which seems to be like 0.78. Okay, let me go on. This I want to state another result. Okay, having to do with recurrence. So this walk is not Markovian, so it is not even clear how you cannot even say that the set of recurrent sites is going to be empty or Z2. So let me write this maybe. This kind of definitions you could guess, but a site is recurrent. I will say a site is recurrent if it is visited infinitely often, and let's call the set of recurrent sites. So that, as I said, by non-Markovianity, it is not even clear of course. Yes, I would tend to believe this this random walk is recurrent, but it's not even clear if D is the empty site or all of Z2 only. These are the only possibilities. So we were able to say something about this. This is also with Omer and Mark. So we can show that D actually is either empty or all the lattice. Okay. I'm going to give a very brief explanation about one of the proofs. So okay, actually I will talk a little bit. I don't have more time, but 3 minutes only about the upper bound. So one of the ideas to prove the upper bound is to look at one of the coordinates of the random walk, and suppose this is the time scale for the old sites. So let's say I could even write x is the vertical sites, well, no, the first coordinate is the x coordinate, and y the notation is not very good because I was using already x for the random walk. So okay, but I think so. I'm thinking about the old sites. Have their own time scale, and this is what I'm thinking as the t here, and this coordinate moves well like some simple random walk. But what we have to do is, or what we did is that we look at special intervals of time. Maybe let me call it this S plus R, where the movement of the coordinate is not very large. So essentially, I will introduce the parameter here epsilon, and ask that normally the movement should be of order square root of R, but I will try to see how many of these time intervals are such that the movement is much smaller than square root of R, because there's this epsilon here, which eventually I will choose as 1 over square root of exactly log n. So this is and what you do in the end is that you show that there are very few points in the time scale of the second coordinate which are not contained in what I define as a slow interval. So this would be a slow interval. So there are very few points which are not contained in the slow interval, few enough to give a good bound for the range at those points. And for the slow interval points, the range is bounded by a square, which is the range of the second coordinate, or the slow coordinate, times the movement of the first coordinate on the interval I, which will also be of order square root of R, and you will get epsilon R. When you add over all these slow intervals, this will give you again epsilon n. Okay, so I think my time is over, so thank you.
Thank you, Alejandro.